Alright everyone, welcome to the sorting module. The very first sorting algorithm that we will be learning and implementing will be bubble sorting algorithm. So this is one of the very first and fundamental sorting algorithm, especially whenever you are not aware of what exactly is sorting and how the sorting is implemented and what are the different techniques and algorithms that are there for implementing the sorting mechanisms. Bubble sorting should be the first sorting algorithm that you should be learning, because the logic behind it will be very easy to implement as well as very easy to understand, so that it will basically give you a great introduction into the understanding of the different sorting algorithms that we will be learning in the next steps as well. Okay, so as part of the problem statement, basically we will be given an array of values. Basically they might be sorted and they might not be sorted. In the end, our aim is to sort the values that are there inside this array either in the ascending order or in the descending order. So whatever the logic that I explain here, I will be writing the logic for sorting the array of values in the ascending order. But whatever the comparisons that we are doing, if you can change that to less than, you will be able to get the bubble sorting algorithm which can sort the values in the descending order too. And the next important thing that you have to know about this bubble sorting algorithm is, bubble sorting algorithm is one of the in-place sorting algorithm. That means that whatever the array we are given, right, in that same array itself we will be able to get the end result in which the values are either sorted in the ascending order or descending order. That's the reason why we call bubble sorting as one of the in-place sorting techniques. Okay, so as part of the bubble sorting algorithm, the main intuition or the process behind this bubble sorting algorithm is comparing the two adjacent values in each and every step. Based on their nature, we may swap those values. Basically, we will start comparing two adjacent values right from the very first value till the very last value we have in the array. While comparing the two adjacent values, based on the way they are arranged in the array, we may swap them according to the sorting algorithm that we are implementing. Okay, based on that statement, let me just try to dry run the bubble sorting algorithm on the array of values that we have here, and let me just explain you the step-by-step process. In the array that we have got here, we have basically 6 values, and the value at index 0 is 1, and the value at index 1 is 4, and the index 2 has a value of -5, and index 3 has a value of 3, and index 4 has 7, and index 5 has -2. So the values that we have here are 1, 4, -5, 3, 7 and -2. Now our aim is to sort these values in the ascending order. By the time we complete the process, we should basically get the array in which all these values are sorted in the ascending order. Okay, now like I mentioned, as part of the definition of bubble sorting, we will start comparing the two adjacent values right from the very first value till the very last value we have in the array, right? So we will start that comparison logic right now. In the beginning, we will compare 1 and 4, right? Since we are trying to sort the array in the ascending order, obviously 1 should come before 4 because 1 is smaller than 4. So we will not swap anything here because the values are already in the expected order. Now what we will do is we will compare 4 and -5. Obviously -5 is smaller than 4, right? So we will swap 4 and -5. So once we swap, the resulting array will have 1, -5, 4, 3, 7, -2. Now we will compare the next two adjacent values, which are nothing but 4 and 3. Obviously 3 is smaller than 4, right? So 3 should come first and 4 should come later. So we will swap values once again. Once we swap the values, the resulting array will have 1, -5, 3, 4, 7 and -2. Now the next two values that we need to compare are 4 and 7. Obviously 4 is smaller than 7, right? So the values are available in the expecting order, so we will not swap it. Now the next two values that we need to compare are 7 and minus 2. Obviously minus 2 is smaller than 7, right? So it should come first and 7 should come later on. That's why we will swap it. Once we swap these 7 and minus 2, right, the resulting array will be 1, minus 5, 3, 4, minus 2 and 7. If you observe here, there are no more elements available in the array so that we can continue this adjacent value comparison. So if you observe the very last index that we have in the array, right, this index has been, updated with the very largest value we have in the array. Observe here, out of all the values we have in the array, 7 is the largest value. That means when we try to compare the two adjacent values right from the very first value till the very last value once, we basically moved the largest value to the last position in the array. Okay, so basically in each and every comparison and swapping, we bubbled up the largest value we have in the array to the last position in the array. Okay, that is the reason why as we are bubbling up the values to the its perfect position, we call this sorting algorithm as a bubble sorting algorithm. Okay, what will happen if we repeat the process once again? That means that we will try to compare the two adjacent values from the first element till the last element once again on the resulting array we have. So if we repeat the same process once again, 1 and minus 5 will get compared. Obviously minus 5 is smaller than 1, right? So we need to swap it. So the resulting array will be minus 5, 1, 3, 4, minus 2 and 7. And the next two elements that needs to be compared are next two adjacent elements, which are nothing but 1 and 3. So obviously 1 is smaller than 3, so we will not swap it. And the next two elements that needs to be compared are 3 and 4. Obviously 3 is smaller than 4, so we will not swap it. And the next two elements that needs to be compared are 4 and minus 2. Obviously minus 2 is smaller than 4, right? So we should swap it. As a result, the resulting array after swapping will be minus 5, 1, 3, minus 2, 4 and 7. Now the next elements that we will compare are 4 and 7. Obviously 4 is smaller than 7, so we will not swap it. And basically there are no more elements that we need to compare for readjusting. As a result, if you check here, the second position from the end of the array, we basically bubbled the second largest value to the second position from the end of the array. So out of all the values we have, 4 is the second largest value. And when we repeated this adjacent comparison and swapping for once, we have moved the largest value to the last position in the array. By repeating the same process once again, we moved the next largest value to next position. That means that second largest value to second position from the end of the array. What will happen if we repeat the same process once again? Let's check once again. Now we will start comparing from very beginning of the array. So minus 5 and 1 gets compared. Obviously minus 5 is smaller than 1, so we will not swap it. And the next two elements that we need to compare are 1 and 3. Obviously 1 is smaller than 3, so we will not swap it. And the next two elements that we need to compare are 3 and minus 2. Obviously minus 2 is smaller than 3, right? So we will swap it. So after swapping, the resulting array is minus 5, 1, minus 2, 3, 4, 7. And we will compare next two values 3, 4. Obviously they are in perfect order, and again we will compare 4 and 7, and 4 and 7 are also in perfect order, and there are no more elements left to compare the next two adjacent elements. So by repeating the process third time, we have basically pushed the third largest value to the third position from the end of the array. By repeating the same logic, that means that if we have, let's just say 5 values in the array, if we repeat the logic of comparing the two adjacent values from the beginning till the end, if we repeat 5 times, basically we will move all the values to their respective perfect positions. That's in the end that basically results the sorted array. Now anyway, on the resulting array that we have here, let me just dry run the logic so that in the end we will basically get the sorted array. So the resulting array after third comparison is -5, 1, -2, 3, 4, 7. Now we will repeat the process once again. So -5 and 1 will get compared. Obviously they are in the perfect order, so we will not swap. Again after that we will compare 1 and -2. Obviously -2 is smaller than 1, right? So we will swap them. As a result, the resulting array will be -5, -2, 1, 3, 4, 7. Again 1, 3 we will compare, they are in the perfect order. 3, 4 we will compare, they are also in perfect order. And 4 and 7 we will compare, they are also in perfect order. So by repeating this adjacent value comparison for the fourth time, we have moved 1, which is nothing but the fourth largest value, to the fourth position from the end of the array. Now if we repeat the same process again, -5 and -2 will get compared. So obviously -5 is smaller than -2, so we will not swap it. And -2 and 1 will get compared, they are in the perfect position, so we will not swap. 1 and 3 gets compared, they are also in the perfect order, we will not swap. Next we will compare 3 and 4. Since they are in the perfect order, we will not swap. Again 4 and 7 will get compared. So there also there is no swapping involved. As a result, after fifth time, the resulting array is -5, -2, 1, 3, 4, 7. Okay, again, since we have 6 elements in the array, we need to repeat the process for 6th time as well. As a result, we will start comparing once again. So -5 and -2 we will compare. Obviously they are in the perfect position. And next -2 and 1 will get compared, they are also in the perfect position. 1, 3 gets compared, 3, 4 gets compared, and 4, 7 also gets compared. And anyway there is no swapping involved because they themselves are in perfect position anyway. As a result, after repeating the same, comparing the two adjacent values for the 6th time, we basically have the completely sorted array. 5, -2, 1, 3, 4 and 7. If you see here, this array is sorted in the ascending order. So as part of the bubble sorting algorithm, what exactly we did? We started comparing the two adjacent values right from the first element we have in the array till the very last element we have in the array. In each and every step, while comparing the next two adjacent elements, based on the way they are arranged, based on the way we are sorting, we swap them. Okay, so those are the steps that we follow for sorting the array in the ascending order using the bubble sorting technique. Okay, in the next steps, I will be writing the pseudocode of it. In the implementation, wherever you see the comparison operation, right? If you perform the vice versa operation, that means if I do greater than, you should use less than. If I use less than, you should use greater than to get the opposite sorting algorithm as well. Now that we know the process behind bubble sorting algorithm, let's just try to write the pseudocode of it, and later on let's try to implement it and analyze the time complexity and space complexity of this bubble sorting implementation. So as part of this pseudocode, what we will do is, first we will simply write a function called bubble sort, and it will basically take the array of integer values in some variable. Here I am naming that variable as a. Immediately, if you remember our steps that I have explained earlier, right? What we will do, we will start comparing two next adjacent two elements right from the beginning of the array till the very end of the array, right? That's why to compare the next two adjacent elements, obviously we need to run a loop. So for that, first of all, what we will do is we will read the length of the array that we have gotten, because whatever the loop statement that we will write, it needs to run for n number of times, right? Where n is nothing but the size of the array. For that, what I will do is, to compare the two adjacent elements, I will be writing a for loop. Okay, so let's just name this as I equal to 1 to I less than, we need to compare two adjacent values till the very last value, right? That's why I am running the loop from 1 to n. In just a minute, I'll explain why I am running the loop from 1 to n. That will make much more sense rather than running it from 0 to n as well. So in each and every step, I need to move on to the next index such that next two adjacent elements can be compared. Now here why I am running the loop from 1 is, if at all, if you remember the array of values, let's just say the values that I have here is 1, 3, let's just say -2 and 10. I need to start comparing two adjacent elements right from the very first value, right? That means if I run the loop from index 1, I'll be able to compare the value at index 1 and index 0. That means in a programmatic representation, I'll be able to compare the value at ith index and I minus 1th index if I start the loop from 1. If at all, if you want to start the loop from 0, that is absolutely fine. But in that case, you need to compare the values at I and I plus 1. So that is something that you have to remember. So as part of the next step, we need to compare the values at I minus 1th index and ith index, right? For comparing, what I will do is I will simply add one if check. If at all the value at I minus 1th index is greater than the value at ith index, that means we have greater value beginning and smaller value at ith index. I minus 1th index has greater value, ith index has smaller value. So obviously greater value should come after smaller value, right? That means that we have to swap it. So for them, if at all that is the case, I will swap the values of array of I minus 5 and array of I. Okay, now by running this for loop once, we would have pushed the largest value to the end of the array. So we need to repeat the same logic for all the values. That means whatever the size of the array that we have, right? That's why whatever this logic that I have written, I'll be running it in another loop. This loop will be running for the number of times that is equal to the size of the array. That's why let's name it as j equal to 0, and it will be executing for all the values. That means that size of the array, and in each and every step I will increment it by 1. So by repeating the same logic whatever we have here, for the second time we would push second largest value to the second position from the end of the array, and for the third time we will push the third largest value to the third position from the end of the array. Likewise, we will basically arrange all the values into its appropriate position. Thus we are getting the sorted array in which basically all the values are sorted in the ascending order. If at all, if you want to implement the same logic to get the array in the descending order fashion, all you have to do is you need to change this greater than comparison to less than, because in the case of array in which all the values are sorted in descending order, the first value should be greater and the last value should be smaller, right? That means if at all, if the value at I minus 1th index is smaller than the value at ith index, then we need to swap it. Okay, so that is something that you have to notice. So very simple, algorithm to understand. In each and every step, we will basically compare the next two adjacent elements, which basically get started from the very first value and ends at very last value. By comparing and swapping, we would push the largest values to its appropriate position, thus getting the sorted array in the end. Okay, so that is the pseudocode behind the bubble sorting implementation. Now let's analyze the time complexity and space complexity involved in this bubble sorting implementation. This time complexity and space complexity also, let's just try to understand it in terms of best case scenario as well as in the worst case scenario. When will the best case scenario of this bubble sorting algorithm will occur? Whenever the array size that we are getting is small. That means that whenever we have only one value in the array, in that case obviously whatever the length reading that we are doing, it will anyway take the constant amount of time because we already have the length available on an array. And after that, whatever the outer for loop that we are running, right, it is running from 0 till the size of the array. That means that if at all, if the array has only one value in it, the outer for loop will basically run only once. And whatever the inner for loop that we have written, right, it is running from 1 to n, right? Obviously n itself is 1, so inner for loop will not even get executed at least once. As a result, the overall time complexity, if we sum it up, the overall time complexity will be constant, which is nothing but order of 1 in the case of best case scenario where we have only one value in the array. To calculate the time complexity in the worst case, right? Obviously, we will assume that there are n number of values in the array that needs to be sorted in the ascending order. So anyway, calculating the length of the array will take only constant amount of time, and whatever the outer for loop that we have here, it will be running for n number of times because it is starting from 0 and ending at n minus 1. That means that we basically run it for n number of times. And whatever the inner for loop that we have written, it also is executing from 1 to n minus 1. Here we are running it till less than n, which is nothing but it gets executed till n minus 1, right? As a result, the total number of times we are running it is nothing but n minus 1. And internally, whatever the comparison and whatever the swapping logic that we have written, right, they both basically will take constant amount of time only to execute. As a result, if we calculate the overall time complexity we have here, it will be n into n minus 1, which is nothing but n square minus n, which we represent as order of n square according to the rules that we have discussed previously. So this is the worst case time complexity, and this is the best case time complexity. If we want to talk about the space complexity, obviously if you see here, one of the advantages of bubble sorting algorithm is that it is an in-place sorting algorithm. That means that whatever the array that we are given, in that array itself we will try to get the end result. That's the reason why anyway whatever the memory that we are consuming in the best case, that means that whenever the array that we have, even if it has only one value, even if it has n number of values, we will try to compare and swap the values in the same array, right? As a result, the overall space complexity will be constant, which is nothing but order of 1 in the case of best case scenario as well as in the worst case scenario. If at all, if you want to calculate the memory taken by each and every line of code, and even if you try to sum it up as well, you will get a constant space consumed by our implementation as well. Okay, since it is one of the in-place sorting algorithm, anyway in the given input array itself we will be able to achieve the sorting array in the end. Okay, so after discussing the time complexity and space complexity, the problem with the bubble sorting algorithm is the time complexity. It is going to take n square units of time. Even if we add one value in the input array, even if we add one extra value in the input array, the amount of time taken by it will be increasing drastically. Anyway, in terms of space consumption, bubble sorting is one of the best ways to sort the array, because irrespective of what is the size of the array, the amount of space consumed by it is constant. And one of the reasons why we will learn the next sorting algorithms is because in the case of bubble sorting algorithm, we are not only comparing two adjacent values, we are also swapping them. So the next sorting algorithm is selection sorting algorithm. In that, we will basically try to eliminate that swapping each and every time. Rather, in the end, once we compare all the values, we will swap the particular value to its appropriate position. So that is the next algorithm that we will be implementing as part of the selection sorting algorithm. So one of the biggest disadvantages of this bubble sorting algorithm is comparing the two adjacent values as well as, if required, swapping. So the amount of computing power this bubble sorting algorithm requires is more compared to any other sorting algorithms that we will be discussing in the future.